I am not Victoria. There's a last-minute change in moderation. So I'm Brian Whedon from Secure World Foundation. Welcome to day 2. It's my pleasure to introduce our keynote speaker this morning. Dr. Francesca Letizia is a space debris engineer at the European Space Agency in the Space Debris Office, where her main tasks include the assessment of general compliance to space debris mitigation guidelines and the development of a metric for contribution of emission to the space debris to improve the space debris environment. Before joining the Space Debris Office, Francesca was the mission analysis engineer at OHB System, where she worked on trajectory design and collision avoidance strategies for satellites and electronic propulsion. Francesca holds a PhD from University of Southampton, where she graduated a thesis on a model for space debris clouds evolution and worked on the development of a tool to assess compliance with planetary protection guidelines. Francesca.
Okay, good morning, everyone. Thanks for the introduction. So today, I would like to give you a brief overview of our report on the global compliance to space debris mitigation guidelines. Okay. So ever since the start of the space age, there has been more space debris in orbit than operational satellites. And as space debris pose a problem for the near-Earth environment on a global scale, only a globally supported solution can be the answer. This creates the need for a set of international accepted space debris mitigation measures in addition to national standards. A major step in this direction was taken in 2002 when the Interagency Debris Committee, the IADC, published its space debris mitigation guidelines. This document has since served as a baseline for non-binding policy documents, national legislation, and as a starting point for the derivation of technical standards. The standardization of mitigation measure is important in order to achieve a common understanding of the required task, leading to transparent and comparable processes. Even if a consistent set of measures is paramount to tackle the global problem of space debris, it's then up to individual nations, operators, and manufacturers to implement them. In order to have an overview of the ongoing global debris mitigation effort and to raise awareness of space activities in general, the European Space Agency has been published a Space Environmental Report. The document is updated yearly and is publicly available. As mentioned, the purpose of this document is firstly to provide a transparent overview of global space activities, to estimate the impact of these activities on the space environment, and to quantify the effect of internationally endorsed mitigation measures aimed at improving the sustainability of spaceflight. To provide a transparent overview of space activity based on observable facts, one can start by analyzing trends such as the historical evolution of the number of objects in the environment. In more than 60 years of space activities, more than 5,800 launches have resulted in more than 44,000 tracked objects in orbit, of which more than 20,000 remain in space and are regularly tracked by the surveillance networks around the globe, including the US Space Surveillance Network. About 26% of the catalog objects are satellite, and only a small fraction, about 2,000, are still operational satellites today. About 17% of the tracked objects are spent upper stages and mission-related objects as launch adapters and lens covers. More than half of the population is made by fragments generated by more than 500 breakups occurred in space, with the two major fragmentation events clearly visible at jumps in this population. Finally, we can see also how the number of objects reflect the improvement in the capability of the space surveillance systems used as source for our report. When new objects are detected due to the increased sensor performance, they can generally not be traced back any longer to an event or source, and a growing category of unidentified objects appear in our plots. So, one of the most relevant observations contained in the last edition of the report is the remarkable change in the launch traffic in low Earth orbit. The number of payloads has reached now 4 times the level of 10 years ago, with a steep increase in particular in the last 2 years. This growth in number is driven by the launch of small satellites, with around half of the satellite launched in the last 2 years having a mass smaller than 10 kilos. This change in traffic is also related to a shift towards a more commercial exploitation of low Earth orbit and a diversification in the actors on stage. A similar trend was observed in GEO many decades ago, and there it led to collaboration among the different actors to ensure an effective exploitation of the available orbital slots. Similarly, in LEO, new collaboration among operators are emerging, as we are hearing in these days, as more and more operators take an active role in promoting best practices to limit the proliferation of space debris. In the environmental report, several metrics are identified that serve as a proxy to measure the global adherence to space debris mitigation guidelines, which have been put in place to protect the space environment from adverse effects such as the Kessler syndrome. These metrics are described in the report considering both their historical evolution and the different performance by different classes of spacecraft. The analysis of the progress made in the last years in terms of compliance should be analyzed considering that the change in traffic that we are observing now, it's only a tiny fraction of what we will experience once the large constellations are operational. So one of the first metrics analyzed in the report is the number of on-orbit breakups. The potential for breakup should be minimized both during the operational phases, for example, by a careful analysis of the failure trees, and after the end of a mission, by releasing stored energy on board as the one in tanks and batteries. Intentional destruction and other harmful activities should also be avoided. Currently, we observe on average 8 non-deliberate fragmentation per year, and this number has not improved in the recent years. 1/3 of the events are related to failure in the propulsion system of the spacecraft, and even if a more systematic application of passivation strategies are contributed to slightly reduce this number, still we see that failure of the propulsion system and the electrical system represent still now a significant contribution to the population of fragments observed in Earth orbits. It is well known that the distribution of these failures is not uniform across the population of the objects in orbit, but rather some specific design have exhibited over time a higher tendency to break up. This is particularly evident if we look at the distribution of the events by cause and by the time between launch and breakup, so as we see now in the slide. And so, whereas for what we call anomalous events, so the separation at low speed of fragments from a parent object, so for these cases, the time appears to be rather uniformly distributed. For certain classes of propulsion and electrical failures, the breakups are clustered around specific times. Design flows can appear at different epochs from launch, but for fragmentation in space, we generally observe a higher incidence of breakup in the first phase of operations, with half of the events occurring within 16 months from launch. This suggests that for the proposed large constellations operating at high altitude, where a repeating design is fundamental to the cost model, the risk of breakups can be mitigated by testing the system at lower orbit before moving to their operational slot. Large constellations also represent an important paradigm shift for what concerns satellite production and testing. This means that we'll be moving from large, almost handcrafted satellites, as for example, one-off payload for scientific missions, to mass-manufactured satellite with much lower cost per unit. On one end, this change could be beneficial. And examples in other industry, as for example automotive, have shown an improvement of reliability figures with the introduction of serious production. In addition, the adoption of smaller and simpler platforms can also improve the reliability figures. On the other hand, the use of commercial off-the-shelf components and the limited redundancy for critical functions may have a detrimental effect on reliability. For this reason, particular attention should be put on testing the platform to verify adequate reliability level, not only in fulfilling the mission objectives, where spare satellites can always be used, but also as a precondition to in-orbit operation compatible with debris mitigation standards and guidelines. Another aspect analyzed in the report is the compliance with post-mission disposal guidelines in the two protected regions defined by the IADC, so the low Earth orbit and the geostationary orbit. Historically, these regions represent where most operational spacecraft reside and where the collision probability is higher. These regions are protected because of their unique nature, which means that it is important to ensure access and operability in this region for future missions, and this requires to define a sustainable use with respect to debris generation. For objects in LEO, the recommended action is to accelerate their orbital decay such that the permanence of the protected region is limited to 25 years after the end of mission. For objects in GEO, it is recommended to move any spacecraft to a graveyard orbit sufficiently above the GEO region and to move rocket bodies into orbits which don't intersect it. Currently, disposal plans and their respective success rate are not systematically shared by operators. Still, thanks to space surveillance data, the activity of a spacecraft can be derived and the orbital evolution predicted. And this is what we do in our report. So for objects in LEO, the residual lifetime is estimated and compared to the 25 years mentioned in the guidelines. And then in this way, we can classify an object as compliant or not. For GEO objects, the evolution over 100 years is checked to detect any return to the GEO-protected region from the orbit where the spacecraft was disposed. So if we look first at the LEO region, we observe that roughly 40% of the total number of payloads operate in orbits which are naturally compliant. So they will re-enter in the Earth atmosphere within 25 years from the end of the mission. In particular, around 78% of small payloads, so below 10 kilos in mass, operate in such regions. This means still that 22% of these spacecraft are left in potentially crowded orbital regions without any maneuver capability. If instead we look at the objects that operate in non-naturally compliant regions in LEO, we observe quite a low level of compliance, with only around 15–25% of the payloads that attempt to comply with space debris mitigation measures. This class of objects is important, as they represent around 50% of the objects in LEO and around 60% of the total mass in LEO. This means that these objects, if not disposed, can fuel the Kessler syndrome because of the mass, and so the number of fragments they can generate, and because of their altitude, which result in a long residual lifetime. The studies of the long-term evolution of the environment have shown how the current level of compliance is not sustainable, in the sense that if the same level is maintained also in the future, we will observe an exponential growth of the population of objects. In the case when also the presence of large constellation in LEO is considered, the study carried out within the IADC in a joint effort across 13 space agencies have shown how a potentially stable evolution of the environment is achieved only in the case where not only the disposal rate is at least 90%, but specifically for constellations object is at least 95%. These target values are very far from the 15% that we observe now. So an important shift in how we deal with disposal operation is needed. If one wants to be optimistic, we can look back to 20 years ago and see that a similar shift is already happening for rocket bodies in LEO. While around the year 2000, the attempt to disposal accounted to less than 20%, we currently observe a value closer to 80%. Even better performance are reached in GEO, where the disposal attempts have consistently been above the 80% level in the recent years. The case of GEO, where there is a clear commercial interest in keeping the operational orbits free from defunct satellites, may be an interesting parallel for large constellations that will also have a similar interest in keeping their orbits clean. So this brings us to the question, what are the desirable requirements to gain access to space from a space debris mitigation point of view? As indicated before, studies of the long-term evolution of the environment show us that addressing these two main aspects that we have just seen, so the fragmentations and the disposal, would dramatically affect the growth rate of the debris population. So for example, if you look at the population of objects larger than 10 centimeters in LEO, we find that in 200 years we would have roughly an increase of more than 3 times in the number of objects, should the current trends in terms of explosion and disposal continue. The successful passivation of any spacecraft would already halve the final numbers of objects. If also a rate of 90% in the successful implementation of post-mission disposal is achieved, the increase of the number of objects over 200 years is only 30% with respect to the 300% of the first scenario. Reaching this level of compliance will probably require to do things differently from now, not only at the operational level, but also in terms of technology. We develop developments, for example, on how to effectively passivate a spacecraft. So while the previous 2 points are already captured in the guidelines and are mostly related to long-term effect on the debris population, the changing scenario in terms of traffic and constellation has an impact also on the short-term operation of satellites. At ESA, we provide operation collision avoidance service to more than 20 missions. And if we look at which objects are encountered by our satellites at lower orbit, we discovered that for this mission, we can observe an increasing contribution coming from intact satellites, such as the one belonging to constellations and all the other small satellites. And this would be the dark blue bar shown here in the plot. This trend will further increase and expand once the more and more constellation will operate in LEO. And this will push operators to reconsider the current setup for collision avoidance activities. For example, last year, we performed 28 collision avoidance maneuvers, and 2 of these maneuvers were performed to avoid operational small satellites, and coordination was required to check their maneuverability status and whether any collision avoidance plan was in place on their side. As you probably have heard, also this year, we had already a similar occurrence that once more made us ask whether emails or late-night calls are the most efficient coordination mechanism and would be still valid in a scenario with 1,000 more operational satellites. A first step to ease the coordination among operators is to promote data sharing. For example, for what concerns the maneuverability status of an object and its predicted ephemeris. And some operators are actually already moving in this direction. A second step is to develop a more automated system for collision avoidance. It is estimated that nowadays global satellite operators spend around $50 million annually on debris impact avoidance activities, but more than 99% of the conjunction notifications are false alerts. The changing scenarios in terms of launch traffic associated to small satellites and large constellations, but also in terms of an improvement of the sensor capability, will generate a much larger number of collision warnings. A possible approach for this is to use techniques such as machine learning to detect conjunction that can result in risky close approach where reaction is needed. So in the upcoming weeks, ESA will launch a global competition on this topic where we will release our historical data on conjunction, anonymized for the purpose of the competition, and we'll invite researchers to put their machine learning algorithm to the test. Of course, the introduction of automated system is not the final solution to the issue of collision avoidance, especially in the case that we mentioned before, where operational satellites are involved. More effective protocols for timely communications are needed in the future, also to ensure a smooth interaction between automated systems and systems with human in the loop, together with the more defined space traffic rules. Also, more transparency in the terms of the risk accepted by missions and on how reaction thresholds are defined may be desirable. Another aspect to consider for what concerns the short-term effect of the change in the launch traffic in LEO is the increase in the average number of payloads delivered by each launch. with multiple launches carrying 30 or even 100 satellites in one go. With so many satellites inserted into orbit at the same time, it's harder for any space surveillance system to distinguish the different satellites, with negative consequences both for the operators, for example, in the case where they cannot communicate to the satellite and they cannot initiate time-critical operations, and also for other operators in general, again, in the case of conjunctions. This last aspect is also relevant in consideration of liability issues in case of damage to other space access. Gaps in the identification process result in the risk of making less effective the applicability of the liability convention. The examples in the past years show how this situation can be mitigated by ensuring communication and data sharing between operators and the space surveillance network. In this scenario, the identification of satellites can be significantly sped up, as in the recent case of the launch of PSLV with more than 100 satellites on board, where the identification of 80% of payloads occurred within 1 month. In other cases, we can see how it took even 6 months to reach the same level of identified satellites. The role of operators here is not only in ensuring proper communication with space surveillance systems, but also to realize which elements in the mission design can significantly impact the ability of identifying and therefore operating their satellite. This is applicable also to small satellites, where we still observe a level of dead on arrival around 10–20%. They may become more and more problematic with the increase in the number of satellites. The aspects mentioned so far all contribute to define how a sustainable space traffic should look like. And different initiatives are currently ongoing to put together these different components, so the short-term effect, the long-term effect, the impact on the environment, the impact on other operators, into a single score. This process is similar to what has already happened in other fields, for example, with the LEED classification in the US or with the energy labeling in Europe. The idea here is to provide a single score that summarizes the impact that a given mission has on the debris environment by considering which mitigation measures are implemented. In addition, it's also evaluated how effective these measures are with respect to evolution of the environment. For this reason, this evaluation is not static, so it's not only carried out at the beginning of the mission for licensing process, but it's dynamic to reflect how the mission operational concepts and mitigation measures are actually implemented, and also to take into account the evolution of the environment. At ESA, we have been working on the development of such concepts for the last years, and we have included this kind of analysis in the last 2 editions of the environmental report, with the motivation that we believe that environmental impact assessment can be a way to strengthen the existing mitigation guidelines. In particular, the metric that we present in the report is based on the potential collision risk posed by a mission to other operational satellites in the case of a fragmentation. And we think that this metric is more effective in depicting the state of the environment than using the simple number of objects. In fact, with the risk metric, you can capture different elements, such as the orbit where a spacecraft is operating, its physical characteristics, the mitigation measures put in place. As any missions operate with certain assumptions in terms of reliability and accepted risk, they cannot be a zero-impact mission. But still, it's possible to identify and quantify how to reduce such an impact and define which level of performance are compatible with the zero maximum accepted footprint on the environment. In addition, since last year, we started a collaboration with MIT, the University of Texas at Austin, and Bright Space and Technology to develop a so-called space sustainability rating, following a call for proposal launched by the World Economic Forum. Also in this case, the purpose is to encourage more responsible behaviors by promoting mission designs and operational concepts that are compatible with the stable evolution of the environment. The approach envisioned for this initiative is to combine in a composite indicator elements such as the risk metric that we present in the report, together with evaluation on the operator actions in fields such as application of international standards, data sharing, and trackability. So in conclusion, the observation from our yearly environmental report show us that the use of space is changing more rapidly than our compliance rate to existing mitigation measures. At the same time, new issues related to how to define an effective space traffic management system are emerging. These make us ask ourselves several questions on how to ensure a sustainable space flight. So, for example, space debris mitigation requires a level playing field to achieve long-term stability. And how can we ensure that this is reflected in standard and licensing rules that are static, so they don't reflect the ongoing evolution of the environment? And another question is, how can guidelines evolve to ensure a more sustainable use of space? And which are the priorities, for example, from an operator point of view? And also, how can we capture better the required behavior? Then we have seen in the slide before there are new elements emerging related to the short-term impact of space traffic on operators. And so one other question is, which is the most effective way to tackle with short-term aspects? And related to this, how far can we go when asking transparency to operators? So should new formal requirements be introduced to promote data sharing and transparency? Would they work for all the aspects that we mentioned before, so the maneuverability status, sharing disposal plan, etc.? So with this question, I conclude, and I'm looking forward to the panel discussion. Thank you.
Thank you very much. That was excellent. One quick question for you. Did you see a difference in trends over time in the compliance? Has it been getting better? Has it been staying the same for the debris mitigation guidelines?
So for certain aspects, yes. For example, for what concerns the, the release of mission-operated objects, we really see very much an improvement after the 90s, where this kind of mitigation measures started to be discussed. But for other aspects, as for example, the one that I mentioned here of the compliance of payloads in LEO, we see still a very, very slow evolution. So, thank you. You're welcome.